RF signals are never perfectly deterministic because noise, interference, and random channel effects always exist. To analyze and design reliable communication systems, engineers must understand uncertainty mathematically. Probability theory provides the foundation for describing randomness in RF signals and system behavior. Probability is a mathematical framework used to describe uncertainty and randomness in systems where exact outcomes cannot be predicted. Instead of focusing on single deterministic values, it models the likelihood of different outcomes occurring within a system or process. In RF engineering, signals are often affected by unpredictable environmental factors such as thermal noise, interference from other devices, and multipath propagation. These effects make it impossible to describe signals using purely deterministic equations. Probability allows engineers to move from exact signal prediction to statistical characterization. Instead of asking what the exact signal value is, we ask what range of values is most likely and how they are distributed. A random variable is a mathematical representation of a quantity whose value is determined by chance. In RF systems, signal amplitude, phase, and noise level can all be modeled as random variables because they vary unpredictably over time. These variables are described using probability distributions, which define how likely different values are to occur. Common examples include Gaussian distributions for noise and uniform distributions for certain interference models. By modeling RF signals as random variables, engineers can analyze system performance statistically rather than relying on exact waveform predictions, which are often impossible in real environments. A probability distribution describes how values of a random variable are spread across possible outcomes. It provides a complete statistical description of uncertainty in a system. In RF engineering, the most important distribution is the Gaussian or normal distribution, which naturally appears in thermal noise and many real-world random processes due to the central limit effect. Understanding probability distributions allows engineers to predict average behavior, variability, and extreme cases in communication systems, which is essential for reliable design. Expectation represents the average value of a random variable over many observations. In RF systems, it describes the long-term average behavior of signals or noise over time. Variance measures how much a signal deviates from its average value. High variance indicates strong fluctuations, which in RF systems often corresponds to high noise or unstable channel conditions. Together, expectation and variance provide a compact statistical summary of RF signal behavior, allowing engineers to evaluate system stability and performance under uncertainty. Probability theory is essential in RF communication because real signals are always affected by randomness. Noise, fading channels, and interference all require statistical modeling rather than deterministic equations. Engineers use probability to design robust systems that can tolerate uncertainty, such as error correction coding, modulation schemes, and adaptive filtering techniques. Without probability, it would be impossible to predict system reliability, signal quality, or performance in real-world RF environments where randomness is unavoidable. In this lesson, we learned that probability provides the mathematical framework for describing uncertainty and randomness in RF systems. We also explored how random variables, probability distributions, expectation, and variance help engineers analyze signal behavior in noisy and unpredictable environments. In the next lesson, we will explore Gaussian noise and see why it is the most important noise model used in communication and signal processing systems. If you found this useful, like the video, subscribe, and follow for the next lesson.